Welcome to Tungal Online Classes. Today we are going to start the topic of electric field. Before this, already fundamentals are completed, I think, to you. So what is that? What is the electrical charge and the properties of electrical charges and Coulomb's inverse square law equation and vector form of the Coulomb's inverse square law and principle of superposition of the charges. All these topics are completed. So from today lecture onwards, we are going to start from electric field. So before going to discuss about the electric field, so already we know that in the lower studies we know about the bar magnet and the magnetic field. Suppose I consider the bar magnet here. This bar magnet is consisting of two poles. So one is the north pole as well as the south pole. So whenever any one of the magnetic needle or a magnetic substance will be placed closer to the given bar magnet, whenever any one of the magnetic substance will be placed very closer to the bar magnet, this magnetic substance will be attracted by the bar magnet. So once again, whenever we consider the bar magnet and surrounded by the bar magnet, if any one of the magnetic substance is placed, that magnetic substance will be attracted by the bar magnet. So whenever the same magnetic substance is placed very far away from the given bar magnet, very far away from the given bar magnet, in that condition, in that situation, this magnetic substance should not be attracted by the bar magnet. From this, what we have to understood, whenever the magnetic substance is located in the first place in this region, that a magnetic substance can be easily attracted by the bar magnet. Whenever the same magnetic substance will be placed far away from the given bar magnet, at that time, even though it is a magnetic substance, that should not be attracted by the bar magnet. That means from this, what we have to understood means, whatever the attracting power of the bar magnet will be there, the attracting power of the bar magnet will be restricted to certain region only. The attracting power of the bar magnet will be confined or restricted to the certain region only. That means whatever the magnetic substances will be there, all these magnetic substances will be located in this region only. Then only all those magnetic substances will be attracted by the bar magnet. So that the region which was surrounded by the given bar magnet, the region which was surrounded by the bar magnet, where its influence will be existing, where its influence will be existing, will be calling as the magnetic field, will be calling as a what? Magnetic field. So now see here, I want to define the term electric field. To define the electric field, I consider a charge capital Q, a charge capital Q will be placed at any point in the space. What we consider here? We consider a charge capital Q. That a charge capital Q will be placed at any one of the point in the space. Whenever that charged particle will be placed at any point in the space surrounded by the charged particle, whatever the charge we are placing, so the space surrounded by the charged particle will be influenced by some sort of energy. Once again, what we consider here? We consider one charged particle which is having the magnitude of capital Q, that will be located at the point O. So whenever any one of the charge will be placed at a given point in the space surrounded by the given charged particle will be influenced by some sort of energy, Whenever another charged particles are entered into that particular region, whatever the charged particles are entered into this region will be felt some electrostatic force. Once again, whatever the another charged particles will be there, if they are entered into that particular region which was surrounded by the given charge capital Q, this type of charged particles are experiencing some electrostatic force. Whenever these charged particles are experiencing some electrostatic force, whenever they will be entered into this particular region we are calling as a what? Electric field. So how can we conclude the definition of the electric field? Means the region surrounded by the given charged particle, in which another charged particles are experiencing some electrostatic force. Such a type of region will be calling as a what? Electric field. So the space surrounded by the given charge, will be calling as a what? Electric field. So this is the definition of the electric field. Now see the next definition. Intensity of electric field or electric field strength at a given point. See here, whenever you consider a given charge will be placed at any point in the space, around the given charge electric field will be produced. Within the electric field, if you consider some different points, say A, B, C, within the electric field, if you consider the three different points, say A, B, C, at each and every point, the strength of the electric field will be different, or the intensity of the electric field will be different. So, how can we define the intensity of the electric field? The intensity of the electric field will be defined as the force experienced by A, unit positive charge, the force experienced by A, unit positive charge at a point in the given electric field is called as intensity of electric field. So how can we define the intensity of the electric field? Means the force experienced by A, unit positive charge at a given point in the given electric field will be calling as intensity of the electric field or strength of the electric field. So the intensity of the electric field or strength of the electric field is represented by, the strength of the electric field is represented by capital E. The strength of the electric field is represented by capital E. So, from the definition of the intensity of the electric field intensity E bar is equal to F bar by Q naught. Intensity E bar is equal to what? F bar by Q naught. Capital E bar is indicating what? Electric field intensity, and F is indicating what? Force experienced by the given charged particle, and Q naught is indicating the magnitude of the charged particle that will be experiencing the electrostatic force at a given point. So here the SI unit of electric field strength is equal to, for the force SI unit is equal to what? Newton, for the charge Coulomb. So what is the SI unit of the electric field strength or intensity of the electric field? Newton per Coulomb or volt per meter. Either Newton per Coulomb or volt per meter. One more formula will be there for the electric field intensity. E is equal to V by D, where V is indicating the potential difference and D is the distance. So that will be coming in the next topic. So according to the formula E is equal to V by D, we will write either volt per meter or Newton per Coulomb. So this is the definition of the intensity of the electric field. Now here electric field intensity E bar will be the vector quantity. Electric field intensity is which type of quantity here? Vector quantity. Vector quantity means what? This electric field intensity or intensity of the electric field will be having both magnitude as well as the direction. Suppose if we consider the positively charged particle, due to the positively charged particle, the direction of the electric field will be acting away from the given charged particle. Suppose at a given point O, I place a plus Q amount of charge. At a given point O, which type of charge we place here? Plus Q charge will be placed. So, whenever we are placing the plus Q charge, due to this charge, the produced electric field will be acting away from the given charged particle. Suppose at the same point O, if you are placing the negatively charged particle, the direction of the electric field at the same point will be acting towards the charged particle. Will be acting towards the charged particle. So here what we have to understand means whether the charged particle will be positive or negative, the magnitude of the electric field will be remain same. But where the difference means in the case of the direction only. If you consider the positively charged particle, due to the positively charged particle, the direction of the electric field will be acting away from the positively charged particle. If you consider the negatively charged particle, due to the same negatively charged particle, magnitude will be remain same at the same point, but the direction of the field will be acting towards the negatively charged particle. So this is about intensity of the electric field. How can we define the intensity of the electric field? It will be defined as force experienced by the unit positive test charge which was kept at a point in the given electric field. That will be calling as either intensity of the electric field or strength of the electric field. It is denoted by capital E. So E bar is equal to what? F bar by Q naught. SI unit is equal to Newton per Coulomb or volt per meter. It is a vector quantity. It is a vector quantity. So this is the basic information about electric field and electric field strength. See the next topic, very important one. Electric field intensity due to isolated point charge. Electric field intensity due to isolated point charge. What is the meaning of isolated charge? So if any one of the charged particle will be separated, from the given system of charges, such a type of charged particle will be calling as isolated charge. Once again, what is the meaning of isolated charge? If any one of the charged particle will be separated from the given system of charges, such a type of charged particle will be calling as isolated charged particle. Such a type of isolated charged particle will be considered. Let capital Q will be indicating. The magnitude of that particular isolated point charge. Already we discussed in the case of the electric field charges, and in the next topic potential and capacitance, all the charges we consider the point charges. And the Coulomb's inverse square law will be applicable for point charges only. Coulomb's inverse square law will be applicable for what? Point charges only. So here in the given diagram, at the point O, I consider a point charge. Capital Q will be placed. At the point O, which type of charge will be placed? Capital Q charge will be placed. And at a point O, whenever you are placing the charge Q, around the charge, electric field will be developed. Around the given charge, electric field will be developed. Already we know the definition of the electric field. If any one of the charge will be placed at a given point in the space, around the charge, electric field will be developed. And whenever another charged particles came into this electric field, they felt some electrostatic force. Already we discussed in the case of the definition of the electric field. So that once you are placing the charge Q at the point O, around the charge Q, electric field will be developed. Within the electric field, which is produced by the isolated charge, I consider a point P, which is at a distance of smaller, and at the point P, Q naught amount of test charge. Q naught will be which type of charge? Test charge will be placed. At the point O, source charge will be placed. That means the charge which is producing the electric field, and at the point P, this is the point P which was existed within the electric field. At the point P, we are placing some test charge Q naught will be placed. So, according to the Coulomb's inverse square law, whenever any two point charges are separated by some distance of separation between these two charged particles, either some attractive force or repulsive force will be existing. So, according to Coulomb's inverse square law, whenever any two charges are separated by some distance of separation between these two charged particles, either attractive force or repulsive force will be developed. So, from the definition of the Coulomb's inverse square law, the magnitude of force of attraction or repulsion will be given by F is equal to 1 by 4 pi epsilon naught capital Q into small q naught by r square. According to the Coulomb's inverse square law, we are writing the magnitude of force either attraction or repulsion will be existing between the two charges is given by F is equal to 1 by 4 pi epsilon naught capital Q into small q naught by r square. Equation number 1. But what is our aim? We have to derive the expression for what? Electric field intensity. We want to derive the expression for electric field intensity. Already we defined the definition of the electric field intensity. What is the definition of the electric field intensity? It is defined as the force experienced by the unit positive test charge. What is the definition of the field intensity? It is defined as the force experienced by unit positive test charge. So that E is equal to F by Q naught. E is equal to what? F by Q naught. From the equation number 1, F is equal to, you know that 1 by 4 pi epsilon naught into capital Q into small q naught by r square. So from this, F by Q naught value is equal to 1 by 4 pi epsilon naught Q by r square. E is equal to what you got finally? E is equal to, you got that 1 by 4 pi epsilon naught into Q by r square. That is the required expression for the electric field intensity which is produced by the isolated point charge. So what is the expression for the electric field intensity which is produced by the isolated point charge? E is equal to 1 by 4 pi epsilon naught into Q by r square. But at the time of a definition of the electric field intensity, you said that electric field intensity will be the vector quantity. Electric field intensity is which type of quantity? Vector quantity. If any one of the physical quantity will be said to be the vector quantity, it will be having both magnitude as well as the direction. Whatever the expression you are derived, this equation will be giving the magnitude of electric field intensity. E is equal to 1 by 4 pi epsilon naught. Q by r square will be giving what? The magnitude of electric field intensity which was produced by the charge capital Q at a distance of small r from this. So that is the expression for magnitude of the field intensity produced by a isolated point charge at a given distance of small r. Now, how can we measure its direction? So for giving the direction, we are using the unit vector. So for which purpose we are using the unit vectors? Unit vector is a vector whose magnitude is equal to 1 and which will be giving the direction of a given vector. So the unit vector will be taken for measuring the direction of position vector r bar. So that the unit vector of r bar can be written as r cap. So r cap is indicating what? Unit vector of r bar. So from the definition of the unit vector r cap is equal to r bar by modulus r bar, that is equal to r bar by small r. From the definition of the unit vector, r cap is equal to r bar by modulus r bar, that is equal to r bar by modulus r bar means what? Magnitude of r bar, that is equal to r. Therefore, the vector form of electric field intensity E bar is given by vector form of electric field intensity E bar is given by E bar is equal to 1 by 4 pi epsilon naught Q by r square, which is the magnitude, which is indicating what? Magnitude. For indicating the direction, we are using the unit vector. So that the unit vector r cap will be giving what? Direction of E bar. So that the vector form of the electric field intensity E bar is equal to 1 by 4 pi epsilon naught into Q by r square into r cap. So this is a vector form of electric field intensity. Again I will write that E bar is equal to 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught q by r square into r cap value is equal to already you wrote. R cap is equal to r bar by r. R bar by r. Therefore, this value is equal to 1 by 4 pi epsilon naught into q by r cube into r bar. E bar is equal to what? 1 by 4 pi epsilon naught into q by r cube into r bar. So this is the vector form of the electric field intensity. Electric field intensity. Now see here, some note is there. Now we derived, see here. So here we derived the expression for the electric field intensity, which is given by E is equal to 1 by 4 pi epsilon naught q by r square. E is equal to what? 1 by 4 pi epsilon naught q by r square. When we will use this formula means whenever the medium surrounded by the given charge must be either air medium or a vacuum. So what is that? Whenever the medium surrounded by the given charged particle should be either air medium or a vacuum, then only we have to use the particular formula. E is equal to what? 1 by 4 pi epsilon naught q by r square. Suppose whatever the charged particle will be considered, around the charged particle some another medium will be there, whose permittivity will be given by epsilon, at that time the electric field intensity at the given point P at a distance of small r in that particular medium will be given by E medium is equal to 1 by 4 pi epsilon q by r square. 1 by 4 pi epsilon q by r square. In the previous case, the medium surrounded by the given charge will be either air medium or a vacuum. In the previous case, the medium surrounded by the given charge is equal to what? Either air medium or a vacuum. At that instant, you wrote that E is equal to 1 by 4 pi epsilon naught into q by r square. Here, the permittivity of the medium is equal to epsilon naught. But here, we consider one particular medium whose permittivity is equal to what? Epsilon. At that instant, at a given point, the field intensity will be given by E is equal to 1 by 4 pi epsilon q by r square. So here we are going to define one physical quantity that is calling as what? Dielectric constant. What is that? Dielectric constant, which is represented by capital K. So how can we define the term dielectric constant or relative permittivity? So it is also calling as a what? Relative permittivity, which is represented by epsilon r. Either we are calling a dielectric constant or relative permittivity. So the relative permittivity is equal to, we are writing that epsilon by epsilon naught. So how can we define the relative permittivity? It is defined as the ratio of permittivity of a given medium to the permittivity of the vacuum. The ratio of permittivity of the medium to the permittivity of the vacuum will be calling as either relative permittivity or dielectric constant. Therefore, now see here. So in the place of the epsilon r, I will write dielectric constant K is equal to epsilon by epsilon naught. From this I will write permittivity of the given medium is equal to what? Epsilon is equal to K into epsilon naught. Epsilon is equal to what? K into epsilon naught. Substitute this value in the equation 2. Therefore, electric field in the given medium is equal to, electric field intensity in the given medium is equal to 1 by 4 pi into, in the place of epsilon we are writing that K into epsilon naught q by r square. Whatever the electric field in the given medium, that is also calling as a what? Electric field intensity in the dielectric medium. E dielectric is equal to 1 by K will be the common. So that 1 by k into 1 by 4 pi epsilon naught into q by r square. 1 by k into 1 by 4 pi epsilon naught into q by r square. So whatever this value will be is equal to electric field intensity in the air medium. Electric field intensity in the air medium. Therefore, E dielectric is equal to 1 by k into E air. E dielectric is equal to what? 1 by k into E air. From this, I will define the dielectric constant k is equal to, it is a ratio of electric field intensity in the dielectric medium to the electric field intensity in the air medium. How can we define the dielectric constant also? It is also defined as the ratio of electric field intensity in the dielectric medium to the electric field intensity in the given air medium. It is also calling as a what? Dielectric constant. So this is the complete information about electric field intensity, that is due to the isolated point charge. Okay. See the next topic. Electric field intensity due to the multiple point charges. Electric field intensity due to multiple point charges. Just now only we completed that the expression for the electric field intensity due to the isolated point charge. What is the meaning of the isolated point charge? Due to the single charge only you derive the expression for electric field intensity. That means whenever you consider the single charged particle or isolated charged particle that is producing the electric field, whose expression will be given by E is equal to 1 by 4 pi epsilon naught q by r square. But in this particular situation, we consider the multiple charges. See here, I consider n number of point charges will be considered. How many number of charges we consider? N number of charges will be considered. Their magnitudes are given by q1, q2, q3 up to Qn. N number of charged particles will be considered, and due to this multiple number of charged particles, I want to calculate the resultant field intensity at the point O. The similar concept we discussed in the case of the principle of superposition of the forces. There we define that the resultant force acting on any one of the charged particle due to the multiple charges will be given by the vector sum of the individual forces. Here also we consider that the same situation we consider. First we consider the charged particle Q1. From the charged particle Q1, the position of the point O will be given by R1. So that I am assuming that due to the first charge Q1, the electric field intensity produced at the point O will be given by E1 bar. E1 bar is indicating what? Electric field intensity produced by the charged particle Q1 at the point O, that is calling as a what? E1 bar. Similarly, due to the another charged particle Q2, at the point O, another electric field will be produced that will be represented by E2 bar. E2 bar is indicating what? Electric field intensity that is produced due to the charge Q2 at the point O, that is represented by E2 bar. Due to the another charged particle Q3, the field acting at the point O will be represented by E3 bar. By the nth charged particle, electric field intensity acting at the point O will be represented by En bar. That means if you observe the diagram, at the point O, simultaneously more number of electric fields are acting. So whenever more number of electric fields are acting at a point simultaneously, the resultant electric field acting at the point O, will be considered as the vector sum of all the individual electric fields. Such a type of principle we are calling as a what? Principle of superposition. What is the meaning of the principle of superposition? If two or more number of fields, two or more number of fields are acting at a point simultaneously due to the multiple charges, the resultant field acting at the point O will be given by the vector sum of the individual fields acting at that point. Such a principle we are calling as what? Principle of superposition. This is about electric field due to the multiple charges. Now, we will see the next concept, electric field lines. What is that? Electric field lines. What is the meaning of the field lines? Already we know the definition of the electric field. What is the definition of the electric field? The space surrounded by the given charged particle. So, for example, at the point O, we assume capital Q amount of charge will be there. Whenever the capital Q amount of charge will be there, this capital Q amount of charge will be producing the electric field around that particular charge. Now, whenever another charged particles are entered, into this region or into this electric field, over this charged particle, some electrostatic force will be acting. Already we know the definition of the force. What is the definition of the force? Force is nothing but either push or a pull, which will cause the change in state of the object. So, whenever over the test charge Q naught, some electrostatic force will be acting, that charged particle will be coming into the motion. While it was in the motion, it was following some particular path. Whatever the path that is followed by the given test charge, within the electric field, will be calling as electric field lines. Once again, listen. We know the definition of the electric field. What is the definition of the field? The space surrounded by the given charge, in which another charged particles will be experiencing the electrostatic force. So here we keep a charged particle capital Q at the point O. As a result, around the charged particle, electric field will be produced. Whenever the another charged particles will be entered into the electric field, they felt some electrostatic force. Whenever the electrostatic force is acting on the given charged particle, from the definition of the force, they will be coming into the motion. Whenever they will be in the motion, they will follow some particular path, so that the path followed by the given test charge within the electric field will be calling as electric field lines. So this is the definition of the electric field line. Okay. Now we will discuss the properties of the electric field lines. Very important one. Okay. Discuss the properties of electric field lines. The first point is all the field lines will start from positive charge. All the field lines are starting from which charge? Positive charge. If you consider any one of the positively charged particle, from these positively charged particles, the field lines are starting radially outwards. That is the first point. What is the first point? All the field lines are starting from the positive charges. And second point, all the field lines are ended with the negative charge. So what is the first point? If you consider the positively charged particle, all the electric field lines are starting from the positively charged particle and they are moving outwards. If you consider the negatively charged particle, all the field lines are ended with the negative charge. Suppose here I consider the negative charge. So all the field lines are coming towards the negative charge, or they ended with the negative charge. So this is the difference we have to understood between the positive charge and the negative charge. If you consider the positive charge, from the positive charge field lines are moving outwards. If you consider the same negative charge, the field lines are coming inwards, or we will say they are ended with the negative charge. Next, third point. Any two lines of forces does not intersect. If you consider any two field lines, any two electric field lines, these any two electric field lines, they does not be intersected. Why? Suppose if you consider any one of the field line, so at any point on the field line, if you draw a tangent, if you consider any one of the electric field line, over the electric field line at a given point, if you draw a tangent, that tangent will be giving the direction of the electric field, at that particular point. Suppose here I consider 2 points P comma Q. So at the point I draw the tangent which came in this direction, so that at the point P, direction of the electric field will be in this particular direction. Now I consider the point Q, here the tangent will be existed in this direction. So whenever you draw the tangent at the point Q, that tangent will be giving the direction of the electric field. So that in a given region, how can we know the direction of the field? Means by drawing the tangent over the given field lines, that tangent only giving the direction of the electric field. So that third point is what? If you draw a tangent at a given point, that tangent will be giving the direction of the electric field at that particular point. Next, fourth point is what? So this is the fourth point we consider. This is the third point. So according to the fourth point, any two field lines does not be intersected. Suppose if any two field lines are intersected, at the point of intersection, if you draw the tangent, there is existing of two tangents are there. So that from the definition of the direction of the electric field, so there are two electric fields are existing at the point of intersection. So in a given field, only one direction will be existing, so that from that definition of the direction of the field, any two field lines does not be intersected. Next, in a region where the field lines density will be more, there the electric field strength is also more. Suppose I consider the field lines like this. See here, I consider the two regions. One is a region A, another one is a what? Region B. If you observe carefully, in the region A, the field lines density will be more. And in the region B, the field lines density will be less. So the region where the field lines density will be more, in that region, electric field intensity will be more, or electric field strength is also more. So what we are saying here, in a region where the electric field lines density will be more, in that region electric field intensity will be more. The region in which electric field lines density will be less, there the intensity of the electric field is also less. So what is the fifth point? The region in which electric field lines density will be more, in that particular region electric field intensity is also more, and the region where the electric field lines density will be less, in that particular region electric field intensity is also less. Next, the electric field lines does not be forming the electric field lines does not be forming the closed loops. The electric field lines does not be forming the closed loops. Suppose if we consider the electric dipole, what is the meaning of the dipole? Means it is a combination of two equal and opposite charges. So here I consider one electric dipole. From the definition of the electric field lines, they will be starting from the positive charge and they are ended with the negative charge. So that the electric field lines are starting from where? Starting from the positive charge and they are ended with the negative charge. So that if you consider the electric dipole, all the field lines are starting from the positive charge and they will be ended with the negative charge only. So the electric field lines does not forming the closed loops, does not be forming the closed loops. So these are the properties of electric field lines. Thank you. The remaining topic we will discuss in the next class.